Okay. Hello, Nish. Who are all there? Okay, Nikhil, Lalita, Tapas, Nikhil. Good afternoon, Nikhil. Atmesh. Hi, Atmesh. Okay, so we'll start. Today we are going to start metallurgy, and today only we'll finish this particular chapter. Fine. So first of all, in this chapter, you see there is like again, it's a theoretical chapter. There are few processes we have that generally you should know. In board also they ask few theoretical things from this chapter. For board exam also it is a bit important. For JEE it is not that much important. If you have little bit of idea of electrode potential, what metal can replace the other metal or not, depending on its electrode potential, then hi Shreyas, hi Aryan, then you can actually do those kind of questions. Okay, but you see this metallurgy, obviously in this chapter we are going to discuss about the extraction of metals, right? How do we extract metal from its ore, right? So this chapter is actually like classified, or we're going to study this chapter into two different part. One, the first part we have is the extraction of metals. Extraction of metals from its ore, from its ores, and alloy. We'll see about alloy. Okay, so this is nothing. In this part, there is not much thing. Only one particular alloy are made up of what all elements. Okay, the composition and all. Sometimes they ask, not in JE, but need they ask. Okay, fine. So extraction of metals. You see, first of all, there are two terms we have in this, and that is mineral and ores. Right. So two terms, two different terms we have here. That is minerals or ores, right? So first of all, you write down the definition of minerals. These are the definition of minerals you write down. These are the of metals, compounds of metals which are which are naturally available, which are naturally available in the earth's crust, earth's crust, and can be obtained and can be obtained by mining. Okay, so these are the compounds of metals which are naturally available in the earth's crust and can be obtained by mining. Okay, what are these things? Ores, right? So these are the minerals. You see the definition of this. These are the minerals from which a metal, from which a metal can be extracted metal can be extracted economically and conveniently. And conveniently. Okay. So ores are the minerals, right? But all minerals are not ores. Minerals are actually all those compounds of any metals which is available in the Earth's crust, right? Uh, like if I take the example of iron pyrite, FeS2, right? FeS2 is a mineral. Okay. Example here I'll write down for mineral FeS2. You write down FeS2 is a mineral. It's not an ore. Why it is not an ore? Because it contains iron into this, but we don't use this particular mineral for the extraction of iron, right? For extraction of iron, we don't use FeS2. That's why iron pyrite, which is FeS2, is not a ore, but it is a mineral. Understood? So here you see, so from this particular thing, we can say that all ores, this point also you write down, the last one here, all ores are minerals, all ores are minerals, but all minerals are not ores, are not ores. Vice versa is not true. We only consider those minerals as an ore from which we can extract the metal economically and conveniently. Right? Iron pyrite, if you use this particular compound to extract iron, you will get iron, but uh, that process is not cost effective. Okay, you have to put a lot of money and it requires a lot of time also. That's why we don't use all those elements or compounds available in the earth crust for the preparation or extraction of any metals, right? So these are the difference of minerals and ores we have. Okay, ores are the compounds from which the metal can be extracted, right? That's the only thing. Minerals are all those compounds of metals. Okay, all those are minerals. Now there is one more term that we have, that is gang. Write on GANGUE, right? These are the impurities. These are the impurities present in the ore. Obviously, when the formation or extraction of metals we are doing with uh, we are doing from a compound, and that compound contains many other elements also apart from the metals which we have to extract, right? So apart from that particular metal, all other elements which is present in the ore, that we consider as impurities, and those impurities we call it as gang, right? GANGUE. Now suppose if I have one ore, right, and from this ore you have to extract the metal, right? So what are the different processes we can have? Processes, when I say, it may be physical processes also, it may be chemical, biochemical reactions also, right? So for any extraction, for any kind of extraction, we have a set of, a set of process we have to follow, but that particular process is not necessary that it will be same for all kind of metal. Okay, remember all these processes that we have, we use this process, we have different for one particular thing, we have different kinds of processes. Those process we use according to the nature or the properties of metals or ores that we are using. Correct. So depending on the properties of metals or ores, we use different processes. Again, one thing that we whenever we do this extraction, we must keep this in mind that the process must be cost effective. It's not like you are putting lakhs of money for extraction of one particular small amount of metal. Okay, so everything is involved into this. What time you are putting in for the extraction, what is the manpower you are putting in, what is the money you are putting in the extraction. If all these if all these things are too much, like you are putting so much of time, you're putting so much of money for extraction of one metals, and then after using that metals, the the revenue that you generate, that must be balanced, right? The money you are putting in and the money you are getting after the making product from that particular metal. So depending all these things will have different processes, and according to the properties we'll use those process for different metals. So we cannot say for every metal this is the process we have to follow. Maybe for iron we have different set of processes. Maybe for aluminium we have different processes. Maybe for copper we have different processes, right? So first of all, what we do, we'll see some examples of some general name of compounds, right? That also they ask sometime in the exam, obviously not in JE but in others exam, like BitSat and Karnataka CET, Comet K and all. They ask this kind of questions. So first of all, we'll see some some uh, common names of compounds, okay, and then we'll see the extraction processes, general extraction processes we'll see, right? So what we are going to do today, general extraction processes we'll see. Like, suppose if I tell you any metal, if you have to extract, first of all, the ores that you are getting, right, that ores you have to grind or pulverize. Okay, grinding means what? Because whenever you get the ores from the earth crust, it is a big lump actually. Okay, it's a big lump. So this you have to grind into small pieces, right? That we call it as grinding, the dissociation of this into small pieces. And when you finally divide this into very fine particles, that process is pulverizing. Okay, so this lump will dissociate into the small pieces, and then we'll do the concentration of ore. So first step is what? I'll write down all those things. I'm just giving you a brief no idea of this thing. Grinding and pulverizing. Then we'll do concentration of ore. Concentration of ore means what? We have to remove all those impurities into that. Okay, removing impurities, we call it as ore dressing also, or concentration of ore also. Now in this we have 3 4 different types of method possible, right? Like we can have hand picking. Hand picking means what? If you can easily distinct the metal and the impurities, you can hand pick those impurities. That we call it as hand picking, right? Again, we have, depending on the nature of the minerals and ores, that is, we have magnetic separation process, right? We have hydraulic processes, which we call it as gravity separation or levitation also. And then after this, when we do the concentration, we'll have this thing, calcination of ores, right? That is a reduction of concentrated ores. When we do calcination or roasting, then after that we have reduction of the roasted calcinated ores, right? So basically this is the general processes we have, and in all these steps we may have 2 3 different types of process, and those process will use according to, again, the nature of metals and impurities. So first of all, we'll see, and after this we'll have one important thing here, that is Ellingham diagram, which is important for board point of view also. That also we'll discuss. Okay, after all these, we'll see 1 or 2 metals extraction, what are the different processes involved, what are the reaction we have into this. So if that will be same for all kind of metals, right? When you understand the general thing, you can go through any book, you will understand, right? So we'll see 1 or 2 examples into that. Okay, and then we'll see what can be done after that. Okay, so anyways, some examples of ores you write down first. This you have to, few in this is important that I'll tell you. Examples of ores. First one is ZnO, zinc oxide. We also call it as ginsite. This name sometimes they ask in uh, state level exams, not in JE. Okay, this is ginsite. Fe2O3, Fe2O3, we call it as hematite. You must have heard this name also. Hematite. Third one, Fe3O4. Fe3O4, we call it as magnetite. Fourth one, MnO2, pyrolusite. Pyrolusite mineral also, we call it as SnO2, cassiterite. Casseterite. Cassiterite, and we also call it as tin stone. Sixth one, Al2O3 dot 3H2O. This we call it as bauxite. Next one is galena or PBS. PBS is what? Galena. Eighth one, HGS. HGS, we call it as cinnabar. And these two names they have asked in the exam, galena and cinnabar. Fool's gold. Fool's gold also they have asked in NEET exam. Fool's gold. This is FeS2. Iron pyrite. Common name is fool's gold. Argentite. Argentite is Ag2S. Argentite. Next one, ZnS. ZnS is zinc blend. Blend. CuFeS2. We call it as copper pyrite, or we also call it as chalcopyrite. Copper pyrite or chalcopyrite. Few more compounds, and the common name that you should know is KNO3. You must have done this in S block also. KNO3 is Indian saltpeter. NaNO3 is chili saltpeter. Next one, AgCl. AgCl is horn silver. This question they have asked. Horn silver. AgCl is important. Na3AlF6. Na3AlF6 is cryolite. CaF2. CaF2 is fluorspar. KCl is sylvine. FeCO3 is siderite. And the last one, ZnCO3 is calamine. Okay, so these are the few common names I have given you. In this, the important one we have is this AgCl, CaF2, FeCO3, ZnCO3. Here we have ZnS, PBS, fool's gold, That is it. This 5, 8, 6, 7 examples that we have is a bit important. Okay, we have seen these kind of questions in a different state level exams, obviously not in JE, and few questions they have asked in NEET exam also. Okay, now, okay, write it down. We'll see the extraction of metals. Okay, now you see, write down extraction of metals from its ore. Is there any kind of puja today here in Karnataka? Yes. Okay, write down. Write down the extraction of metals. The extraction of metals from its ore involves the extraction of metals from its ore involves four different processes. Involves four different processes. The name of the processes are, the first one is grinding and pulverizing of ore. One by one we'll see this. Sometimes in the board they ask the definition of this also. What is grinding? What is pulverizing? Like this. Okay. Second step is concentration of ore. Concentration of ore I'm writing down. It does not mean the concentration is that concentration of solute and solvent that we write. Concentration of ore means what? This we also call it as ore dressing, right? So we used to remove impurities here or gang into this process. Okay, and the ore that we get after this process we call it as concentrate. Okay, third step is the reduction of concentrated ore into crude metal. The ore that we get from in the second process that we call as concentrate or concentrated ore. So reduction of concentrated ore into crude metal. Fourth process is this. Okay, and then the metal that we get here, crude metal, we have to do the refining of that crude metal. So last step is refining of crude metal. Okay, so one by one we'll see these methods, what is this methods definition and all. So in this, the first method you write down, definition you must remember. Okay, the first method here you write down, that is grinding and pulverizing. Amog is there, Aditya is there, Snigdha is there, Sayuja, Shreyash, Aryan. Okay, where is Amog? Aditya, any information you have? Okay, okay, Aditya, fine. Okay, write down this grinding, write down ores obtained from the earth crust. Write down into this, ores obtained from the earth crust usually have big lumps, or you write down ores obtained from the earth crust are usually occur, write down like this, ores obtained from the earth crust are usually occur in the form of in the form of big lumps, big lumps. Right on, these lumps are broken or crushed into small pieces. These lumps, these lumps are broken or crushed into small pieces by small pieces by jaw crushers or grinders. By jaw crushers or grinder, these are the machines basically that we use. Okay, grinding machine that we call it as grinders also, and jaw crushers also one same kind of machine, right? So usually by jaw crushers or grinders, this process is known as grinding. Next line, write down here, when you have this lump, right, when and if you do the grinding of it, this will dissociate into small pieces like this. You'll get the small pieces of this lump, right? Now, when you do the pulverizing of it, after this, the small pieces that you write down here, the small pieces obtained are reduced to fine powder. The small pieces obtained are reduced to fine powder, fine powder. This process is known as pulverization. Okay, pulverization. So after pulverization, or when we pulverize this, we'll get small fine pieces of these elements, right? So this process we call it as pulverization or pulverizing of ores, right? So for grinding we use, here we are using jaw crushers or grinders. For pulverizing we use ball mill. Okay, it is not important, but we use ball mill or stamp mill also. You can use this. Basically it is a kind of uh, device or machine we have that we use to reduce the size of the particles. That is it. Okay, name of this machine you don't have to memorize basically. So this is the first step. We'll get the fine powder here of the lump or ores that we get from the earth crust. Correct. Okay, now Amog is there. Fine. Now the next step is what? The concentration of ore or ore dressing. So next step you write down, the second step, second process is the concentration of ore. Concentration of ore, which we also call it as ore dressing, right? Write down into this. Write down the process of removing, the process of removal of gangue, you write down. The process of removal of gangue, which is the impurities basically. The process of removal of gangue from the ore, the process of removal of gangue from the ore is known as concentration of ore or dressing of ore or benefaction process. Benefaction. Benefaction process. Usually we don't use this term, but since it is there, I'm giving you this. Okay. So concentration of ore dressing, benefaction, or these are same thing, right? Write down in this the concentrated ore we get into this step. The concentrated ore we get in this step is known as concentrate. The concentrated ore we get in this step is known as concentrate. Okay, concentrated ore or concentrate. Now, like I said, just now I've given you that what we do in this concentration of ore, what is the uh, thing we are going to do into this step. The thing is what? We have to remove the impurities. Correct? Removal of impurity is nothing but concentration of ore. Now, for this removal process, we can also use 3-4 different methods. Like I said in the beginning, depending upon the nature of minerals, the nature of ores, right? Depending on that, we have different process involved to get concentrate or for the process of concentration of ore, right? The first thing, which is the easiest one we have in this A, write down into this under this point, under this second step. The first method for the concentration of ore is hand picking. Okay, just to write down hand picking. In this also you can understand with the name only. If you can easily distinct the mineral and ore, then we can hand pick those minerals and remove those impurities, right? Minerals are generally when I say minerals in this, it means we are not talking about ores, we are talking about all other elements which is present in that sample, okay, apart from the ore material that you have. Okay, so write down into this, when the impurity is present, hand picking, just one line you write down, when the impurities present are distinct from the ore, when the impurities present are distinct from the ore, so that they can be easily differentiated by our eyes, so that they can be easily differentiated by our eyes, then we can handpick those impurities. That's what the hand picking. We can hand pick those impurities. So under concentration of ore, first is this, which is generally not very useful. Okay. Second one is what? Second one is gravity separation. Gravity separation method, and we also call it as levitation. Levitation is the another term we use for this process. Okay, right on to this. See, like the name suggests, gravity separation. Okay, so this particular method we use when the specific gravity of metal and gangue is different. Right? Write down this process we use. This process we use when the specific gravity of metallic ore, when the specific gravity of metallic ore and gangue particles are different. Gangue particles is different, sorry. Metallic ores and gangue particle is different. This is used only for heavier ores. Only for heavier ores like SnO2, you say. For SnO2, which is cassiterite. Okay. This is Casseterite, cassiterite, or hematite, which is Fe2O3, Fe2O3, HAEMETITE. For these ores, we can use this particular method. Now you see in this what happens. I'll just draw a diagram in the next slide. You see. See, we have an arrangement like this here. We have a table like this. Okay, and in this table there is a system we have. Funnel kind of thing is there, and here we have an arrangement of flow of water. From this we produce water here, right? And from this funnel we used to put the uh, ore, right, which is crust, actually the crust ore, which this crust ore we get in the first step, grinding and pulverizing that we have, right? So when I put it here, and here there is an arrangement like this, right? And in this we have a raffles. Raffles means there's a net kind of thing is there which can you know hold the impurities. You see here, there is a net kind of thing here. It is arranged. So I'm just giving you a brief idea of this, not the exact diagram we have here, right? So this is, we call it as raffles. Okay, and then here we have a beaker where this, okay. Now you see what happens here. This is the water we are putting in, There's a flow of water which is going like this, okay, and crust ore is going over here. Since there is a difference in the specific gravity, so the mineral that you have here, or the ore particles that you have, okay, that will stuck here into this raffles, which is nothing but a net kind of arrangement is there, which can hold the ore particles here, and all those gang that will settle down here with this water and flows from this side and get down into this beaker. Okay, this is nothing but here we have the mixture which contains gang impurities plus water H2, right? And what we do when we flow this water, this is a table we have, okay, and this table we have an arrangement so that we can continuously shake this table so that there will be settling of this ore, this gang material here, and that will come uh, through this with this water into this beaker. Okay, so what happened into this, just to write down the continuous vibration of table, the continuous vibration of table results lighter particles, lighter particles moves downward, and heavier particles heavier particles are left behind in the barrier. Barrier means the raffles that we have here in this net, it will be stuck, and these impurities will go down with the help of water. So this is a table we have, which we use to shake continuously for this process to possible, right? So this we use, like I said, there are different processes. This we use when there's a difference in specific gravity of the impurities and ore that we have. Okay, so this is the second process that we use for the concentration of ores. Magnetic separation, the third one we have, and this one you must have the idea of it. What we when we use this magnetic separation method. Okay, so write down this magnetic separation. So what we do in magnetic separation, write down, it is used for magnetic and non-magnetic impurities. It is used for magnetic and non-magnetic impurities. This method is useful. This method is useful for the separation of chromite for the separation of chromite ore. Chromite ore is this FeCr2O4 from the separation of chromite ore from siliceous impurities. Siliceous means the impurities of contains silica. Siliceous impurities, where, like I said, this is the magnetic thing, and this one is non-magnetic. So what happens in this, the arrangement that we have here, we have two roller here, I'll try to. And these rollers contains one magnetic, uh like there's a magnetic belt we have here, like this. And again we have a funnel here from which we used to put the crust ore into this. Here we'll have the crust ore. So all these crust ore, just a second. See, these are the crust ore we have that we are putting in. And this crust ore contains the impurities where we have magnetic nature, right? So those magnetic particles, the magnetic particles that we have, that will be in contact with this belt for a longer time, and that will come down over here because of the magnetic nature, and non-magnetic particles will separate here only, and that will fall down over here, right? So this is what here that you get here, that will be the magnetic impurities, right? And this one here that you get, that will be concentrated ore. Concentrated ore. It may be a reverse also, right? If the if the ore is has the magnetic property, then here we'll get concentrated ore, and the impurities, if it is non-magnetic, then here will be the non-magnetic impurities. Okay, so this is very simple and easy to understand, right? Understood? So this we call it as magnetic separation. Okay, this is what, this is the roller we have, which is connected with a motor and it moves. This is the belt. This roller is actually, it is magnetic roller. Okay, so this is the another third uh, method for the concentration of ore. Now the next one in this, the next one here, we have two more methods into this. Next one is froth flotation process. Froth flotation process. Third one. Okay, write down in this, just to write down quickly because we have a lot of theory into this chapter. Okay, write down. The method is based on, it is based on wetting, WETTING, wetting characteristics of ore and gangue, GANGUE, wetting characteristics of ore and gangue by oil and water. Whether this ore or gangue gets wet with oil or water or not. Okay, this method is used for, write down, in short you write down, used for the concentration of sulfide ores. Okay, this you must remember, sulfide ores. For example, we have galena, PbS. We can have copper pyrite, CuFeS2, or we can have zinc blend also, ZnS. For all these three different ores, we can use this particular method. Okay, right on. In this process, a suspension of finely powdered ore and water is made. Will made a suspension of finely powdered ore and water finely powdered ore and water, depending upon the nature of ore, depending upon the nature of ore, we use we use various additives, various additives such as frothers, froth stabilizers, frothers, froth stabilizers. Write on this: FROTHERS, frothers, froth stabilizers, or collectors, COLLECTORS, collectors. See, what are frothers? Frothers, froth stabilizers, and collectors. See, frothers are, just wait. Frothers are frothers. These are the compound such as pine oil. Example is pine oil, which we use for, which helps in the formation of froth. Okay, because froth, see, actually the overall process of this is what, when the froth forms, this contains the impurities. Okay, so when you will have this, the whole setup is like this. We have a system like this, and there we have a pedal kind of thing here, and this we can rotate, right? This is fixed here, and this keeps on rotating like this. Okay, so when this moves, and here we have the solution, here we have the um, ore particle we have here. So when this continue, when you agitate this particular mixture here, then it forms froth, and that froth contains the various impurities with it, and which is there in the upper layer above here, the froth that forms. Okay, so which you can with the, and those froth can be easily skimmed off, right, on its own, and from that you can easily remove the particles there, right? That is what the process we have here. So depending on the nature of the ore, whether the formation of, if the formation of froth is difficult, then we add frothers into it. What are frothers? Frothers are, an example of this is pine oil. Pine oil we use, which helps in the formation of froth. Okay, so these are frothers. Froth stabilizers are what? Because frothers are can be easily skimmed off, so we should use some froth stabilizers also into this. So example of this, you write down froth stabilizers, which stabilizes the froth, right? That is, we have cresol. Cresol is an example of froth stabilizers. You must remember this, froth stabilizers. Aniline is also the another example. Aniline cresols are the froth stabilizers, right? Collectors are what? Collectors, you write down the examples of collectors. It is ethyl xanthate. This example they have asked once. Xanthate, ethyl xanthate, potassium ethyl xanthate, potassium ethyl xanthate, xanthat. What this collector do? Actually, this enhancing the non-wettability of the mineral particles. It enhances the non-wettability of mineral particles. Okay, so few examples I'll give you. Now, just two, three lines we write down. On rotating the paddle, on rotating the paddle, the formation of froth takes place. The formation of froth takes place, which carries mineral particle with it, which carries mineral particles with it. Mineral particles with it. The froth being lighter, the froth being lighter floats on the surface, being lighter floats on the surface and skimmed off, which we can dry for recovery of mineral particles. Okay, now the next last process for concentration of ores we have here, that is leaching. Leaching. Leaching, we also call it as hydrometallurgy. Leaching or hydrometallurgy. Write down into this. Leaching depends upon difference in chemical properties of ore and gangue. Leaching depends on the difference in chemical properties of the ore and gangue. It involves it involves the treatment of powdered ore. It involves the treatment of powdered ore with suitable reagent. Powdered ore with suitable reagent. This reagent actually it can be anything. So when you write down suitable reagent, in bracket you write down acid, base or other chemicals. acid, base, or other chemicals. Okay. So basically, whenever you have any ore, right, and if the mineral and ore is like their chemical properties are different, then we use this process. Okay, we can use various chemical reagent for this process to take place. Like for example, you see if you have bauxite. Okay, so just to write down two examples I'll give you, this is important. Leaching of bauxite ore, in this way write down examples. Leaching of bauxite ore, this process we call it as Bayer's process. Remember that. Bayer's process. Now in this, what happens? This bauxite ore, which is Al2O3 solid, it is allowed to react with. I'll just write down the reaction. Okay, uh, I'm not giving you theory, the line of all these. Al2O3 alumina solid reacts with the aqueous, the solution of sodium, the hydroxide, sodium hydroxide we have. It is aqueous solution of this, and obviously we have some amount of water here present. When this reaction takes place, it forms sodium meta-aluminate, which is 2Na Al OH whole 4, aqueous. This we call it as sodium meta-aluminate. Okay. Now this solution is cooled and its pH is adjusted, right? So what happens? This NaAlOH NaAlOH whole 4, right? Its pH decreases a bit, right, by dilution or neutralization. pH of this solution decreases a bit by dilution or neutralization, right? And we allow CO2 to pass through. So what happens is NaAlOH whole 4 minus, in this neutralization takes place, or upon dilution its pH decreases, CO2 passes through, then this dissociate in the form of AlOH whole thrice solid plus OH minus, hydroxide ion goes off, right? Now this AlOH whole thrice, I'll write down here the last reaction. When you heat this, right, this is solid. When you heat this around 1473 or 1500 Kelvin, right, then this dissociates into alumina, that is Al2O3 solid plus H2O plus H2O. This is the concentrated ore we have here, alumina. Like this, the concentration is done of alumina. So basically, in this chemical reaction, we use the chemical properties of various compounds, ores, minerals, and then according to that, we'll use some suitable reagent to purify the ore that we have here. Right. So these are the four processes we use for the concentration of ores. Write down this. Next is the third step is reduction of concentrated ore. The third one is reduction of concentrated ore. Now, reduction of concentrated ore that we get in the second step, that is ore, we call it as concentrated ore. Reduction of that we have to do in the third step. For this, I'll directly come to the important point here. For this, we use generally two different processes. One is cancellation and other one is roasting. So first of all, you write down calcination of this. Okay, what is calcination? Definition of calcination you write down. It is the process in which the definitions are important. Okay, so you must remember. It is a process in which the ore is heated strongly. The ore is heated strongly in absence or limited supply of air. In absence or limited supply of air. Right? And supply of air at a temperature at a temperature that the ore does not melt below the melting point. We use the temperature where the melting is not taking place for the ore. That we have to take care of. So limited supply of air if you have, then it is calcination, and other one, like I said, that is roasting, which is when we have excess of air. That is the only difference. Okay, so you see here the reaction. Few examples I'll write down. In this, what happens? The volatile component goes off. When you heat this strongly, the volatile component, like you see CO2, SO2, H2O, goes off. This is what happens into this. You see, when you have this hydroxide of iron, when you heat this, in this H2O goes out, we'll get oxides of iron and H2O goes out, 3 moles of this. If you have CaCO3, when you heat this CaCO3, it forms CaO and CO2 goes off. Okay. So this is what the cancellation is. Now, the next method in this only we have, that is roasting. ROASTING. Right? B. This actually, in this process, the ores are heated strongly. In this process, the ores are heated strongly in presence of air, in presence of air at a temperature at a temperature below its melting point. So in this, usually what happens, ores converts into its oxide. For example, you see, if you have HGS, and when you heat this with oxygen, it forms HgO plus SO2, 2SO2. You get the oxides of acid. If you have ZnS, it forms 2ZnO plus 2SO2 again. Sometimes sulfide also we use into this. PbS plus 3O2. It forms what? PbO plus 2SO2. Right. Sometimes what happens? Insoluble sulfide ore also converted into corresponding sulfate. Okay, which is soluble, which is water soluble. So this is CuS plus 2O2 gives you CuSO4. So this is insoluble sulfide ore, and this is water soluble. This is how this process takes place. If you have any sulfide ores, it converts into its oxide. Okay. Sometimes the sulfide also behave as an reducing agent here. The example is this, and here it sometimes convert into its sulfates, which is water soluble. Okay, so like this the roasting process takes place. Among you see the third reaction. This sulfides are behaving as a reducing agent. You see oxygen is getting reduced. In all these reactions, you see oxygen is in zero oxidation state, and right side it is in -2 oxidation state. So oxygen is getting reduced, and that's why the reduction of oxygen takes place. And but the title is reduction of ores. No, actually, I haven't given you the full thing here. The reduction of concentrated ore into its oxide, actually. Okay, I haven't given you here. See, this should be reduction of concentrated ore into its oxide. So better you write down concentrated ore into its, yeah, the meaning is half then, right? Into its oxide, or you write on metallic oxide. That would be better. Metallic oxide. So it does not mean the reduction of ore is taking place. Uh, the reduction is taking place here, and the metal is converting into its oxide. That's the thing. Okay, so better you write down reduction of concentrated ore into its metallic oxide. Fine. Okay, so these are the two process we use for the reduction of concentrated ore into its oxide. So basically, first we have the lump. We'll do the grinding of that. We'll get fine powder of that ore. Then we do the concentration of ore, where we remove the all those impurities, gang and all. And then we do the reduction of concentrated ore into its oxide. So finally, we are forming the oxides of the metal, right? Now from this you see the last step we have here, that is the reduction of calcined or roasted ores into its metal. Now you see these are the metals we are getting, right? Right. Here you see all these metals is in +2 oxidation state, right? When the reduction of this metal oxide or sulfates takes place, this converts into what? Converts into metal. That's what the last step we have here, which is the fourth step, which is the reduction of, write down the fourth step, reduction of roasted or calcined ores into metal, right? So we'll get this metal, and then we'll do the refining of it. That is it. Okay. Now when reduction it is there, right? So we know the electrode potential of various metal when it reacts with that. So one metal can displace others according to that. The basic idea is that only. Okay. One point in this you write down. The extraction of metals from its oxide, here you write down, the extraction of metals from its oxides by a process involving by a process involving by a process involving melting is known as smelting. Okay, by a process involving melting, in which the melting takes place, that process we call it as smelting, Smelting. So reduction of a metal oxide by a process in which the melting takes place, that process we call it as smelting process. Okay, write down the roasted ore write down the roasted ore contains non-fusible impurities contains non-fusible impurities such as silica, silicates, metallic oxide, etc. Roasted ore contains non-fusible impurities such as silica, silicates, metallic oxide, etc., comma, comma, an additional substance is added to the furnace. An additional substance is added to the furnace during the process of smelting. This, smelting process, I guess they have asked this question in board exam. Okay, so definition, that's why it's important. Okay, and when you write down all these definitions, so you must write down one example also, that is important. Okay, an additional substance is added to the furnace during the process of smelting during the process of smelting to remove those impurities to remove those impurities is known as flux. Flux, right? Which forms the those additional compound that you add during the process of smelting. We call it as flux. Flux. What it does, this flux actually combines with those non-fusible impurities, okay, or gang that you have, Gangue. This is what? This is non-fusible, right? So when flux combines with this gang non-fusible, it forms slag, which is actually fusible, and we can remove this easily. That's the purpose of adding flux into it. So definition of flux you must remember. Okay. Now next thing in this, since it is a reduction of roasted ore we have, so there are chemical reactions into this. So write down, this reduction can be done in three different ways. Like here also we have three possibilities. First one is chemical reduction. Chemical reduction. Chemical reduction, you see, in this we can use carbon as the reducing agent. Carbon as reducing agent, right? For example, you see any metal oxide, Metal, metal oxide. When reacts with carbon, when you heat this, it gives you metal plus carbon monoxide, CO. Okay, so like you see few examples here, PbO plus C, you heat this, you'll get lead plus carbon monoxide. Similarly, ZnO plus C, heat this, you'll get Zn plus carbon monoxide. Like this, we can have many other examples. SnO2 plus C, you heat this, you'll get metal plus 2CO. Right. So these are the metal you are getting. So last step in this will be what? That will be the refining of this metal. That is what the purpose we have, right? We have to get the purest form of the metal, purest possible form of the metal. Okay. So okay, there are few reactions also. There we use carbon monoxide as the reduce. This is the one thing where carbon is a reducing agent. We have also few reactions in carbon monoxide as reducing agent. We can use, that is, you see three reactions. I'll give you Fe3O4 plus CO, and when you heat this, you'll get iron plus 4CO2, right? We have CuO plus CO. When you heat this, you'll get copper plus CO2. Okay, so this is the first reaction we have, that is chemical reaction. Aluminium also you can use as a reducing agent. Okay, like you see Cr2O3 plus aluminium, it forms what? Al2O3 plus chromium. This is what we get. So these are the few reactions basically where the reduction takes place. Okay, now there are few reactions in which the B second process we have, that is auto or self reduction process. Okay, auto or self reduction process. Like the name suggests, in this process we do not require any reducing agent. Okay, so the first thing you should write here, no reducing agent required. Okay, in this you write down the sulfides of less electropositive metals. This is just a displacement reaction according to the electrode potential. Okay, ZnO plus C. What happened, Nikhil? What is the doubt? That also you can write ZnO2 ZnO plus C gives you Zn plus CO2. That is also possible. Actually, two steps reaction we have. ZnO plus C gives Zn plus CO. Again, ZnO plus CO gives you Zn plus CO2. Right? When you add those, you see CO gets cancelled. So that also you can write. It's not a big deal. See, CO2 when you have excess of, see, when carbon oxygen reacts, okay, when excess of oxygen we have, then we'll get CO2. Otherwise, first, in that also first CO forms and then CO2 will get. Okay, so that also you can write, not a big deal. Anyways, so auto and self reduction, write on to this. Like I said, that this reaction is based on the electrode potential of the metal. So in this, you write down the sulfides of less electropositive metals, the sulfides of less electropositive metals, such as mercury, copper, lead, tin, the sulfides of less electropositive metals, such as mercury, copper, lead, tin, are reduced on itself. Are reduced on itself. Few reactions you see. HGS plus 3O2. 2HGS plus 3O2 gives 2HGO plus SO2. Right? And then again, this HGO combines with cinnabar, which is HGS, forms Hg plus SO2. Right? So this is the metal you are getting. In this also, you see, actually this reaction takes place in two steps. First we'll get HGO, then this again converts into Hg. Similar reaction you see, 2Cu2S, copper glans we also call it as, okay, 3O2 gives you 2Cu2O plus 2SO2. Here also we should write 2SO2. And then this 2Cu2O reacts with Cu2S, gives you 6Cu plus SO2. Two-step reaction again. Do you see the metal you are getting? So like this reaction takes place. Okay. Now the third AB we have done. The third process in this is electrolytic reduction. Electrolytic reduction method. Write down when the chemical reaction method, when the chemical reaction method is not applicable, when the chemical reaction method is not applicable, then we use electrolytic reduction. Then we use electrolytic reduction. Depending upon the oxide, depending upon the oxide, this process may take place at high temperature, at high temperature, in bracket you write down in absence of water, may takes place at high temperature in absence of water, or or at low temperature using water. Okay, so actually this process may takes place in two different conditions: high temperature without water and low temperature with water. Right, so this we use high temperature when the oxides are stable. Oxides are stable, like in the case of oxides of alkali or alkaline earth metal. Alkaline earth metal. So basically the oxides of alkali and alkaline earth metal are stable. So for those oxides, we use high temperature without H2O for this process. Right? Since it is stable, so to dissociate this, we require high temperature. That's the reason. Okay? Write down in this, write down, when the oxides are heated at high temperature, when the oxides are heated at high temperature, the metal reacts with carbon to form carbides. Okay? These metals react with carbon to form carbides, and hence such metal cannot be extracted by reduction of their oxides. By reduction of their oxides with carbon, you write down. And such metals cannot be extracted by reduction of their oxides with carbon. And hence, for those metals, and for those metals, we use electrolysis process, electrolysis process, lysis process, in which the metals are liberated at cathode, in which the metals are liberated at cathode. Right? So for all these stable oxides, alkali and alkaline earth metal, if you try to reduce this with the help of carbon, right? So you require high temperature for this reaction. Why? Because the oxides are stable. So when you heat these oxides at high temperature, then the metal may get free from oxygen, but that metal will combine with carbon to form carbides, and hence the isolation of metal is not possible in this. Okay, you are not having oxides, but you will have carbides then. Okay, so for those kind of metals, we don't use carbon reduction method, but we use electrolytic reduction, right? And electrolytic reduction, that we have where metals will get at cathode, right? Reduction takes place at cathode, so metal will get at cathode, right? So there are many reaction into it. Fusion will take with NaCl, okay, and then reduction. That basically electrolysis process we have, that you keep in mind. Okay, so these are the basically the process we have for the extraction of any metals, right? This is the fourth process we will use for any metal to extract. Depending on the property, we use calcination or roasting. For concentration, we use grinding, pulverization, or we use what? Or we use leaching, or we can use the gravity settling process, or we can use the magnetic separation method. Okay, anything. All these processes we can use according to the properties of the ores and the minerals or impurities we have. Okay, so for different metals we may have different process, but all those process will be one of these only that we have already discussed, right? So anyways, this is the general method of extraction of any elements, any metals we have done, right? Now the last thing in this is the purification or refining of metal. Okay, so the last thing you write down, purification or refining of metal. The last into this, the metal that you get here, we used to purify that or refine that. So for that, you write down the last thing, purification or refining of metal. Okay. So in this you write down, this method is used for the purification of this method is used for the purification of this method is used for the purification of metals like copper, zinc, silver, gold, tin, copper, zinc, silver, gold, tin, nickel, aluminium, etc. Okay. Now in this you write down a few information you should keep in mind. For cathode, it is made up of it is made up of thin strip thin strip of pure metal. Whatever metal we have to purify, pure metal of that will take thin strip of pure metal will take into that. Okay, and the metal should be same which is used. This thin strip will be of the same metal which is used to purify. Okay, anode here made up of large slab of impure metal of impure metal. Means this slab is made up of the metal which is to be refined. Electrolyte that we use here, purification we do by the electrolysis method. The electrolyte that we use here, it will be the aqueous solution of a suitable salt of the same metal. So at cathode, you see the reaction that takes place here at cathode will be M n plus n electron gives metal solid. At anode, the reaction will be two types of reaction here, M n plus n electron, and the impurities that you have here, X n plus, gives you half of X2 plus an electron. This X is nothing but the impurities, right? So this reaction, we want this reaction to be there, to takes place, right? Because when this from the large slab that you have, let me draw this also. Okay, this is the electrolyte, and in this there is one cathode and one anode. And anode we write on the left side. Sorry, this should be like this. This is anode, and cathode is a thin strip, so it is this. And this is connected with the external source here. This is the anode we have, made up of impure metal. Cathode, it is pure metal. So here the reaction is this, anode the reaction is this. Okay, and what we want from this particular slab, this reaction takes place, and this electron is taken up by this ion here, and the metal deposited will get here, solid metal. Okay, so now in this one, the anionic part, right? There is a concept of that we have studied in electrochemistry. That let me tell you, there is one concept of overpotential, right? One concept of overpotential. That concept we can apply over here. Okay, but we are not going into all those things because that is not required. The only thing you have to keep in mind here, write down the anionic part of the electrolyte is to be the anionic part of the electrolyte is to be selected in such a way the anionic part of the electrolyte is to be selected in such a way that the anodic reaction 2, this is the first reaction we have of anode, and this is the second reaction of anode, that the anodic reaction 2 does not take place, and hence the metallic, sorry, just a second, and hence the metal starts depositing at cathode. The metal starts depositing at cathode. One note you write down here, the metallic impurities having lower oxidation potential the metallic impurities having lower oxidation potential lower oxidation potential then the metal are are separated out in the form of anode mud, and that anode mud we can show over here. This is anode mud. Okay, so whatever the anionic part of this electrolyte will take here, their oxidation potential must be more than the impurities, more than the oxidation potential of impurities here, so that this reaction won't takes place, right? This second reaction won't takes place. This reaction will takes place, and then the metal starts depositing by this reaction on cathode. That's what the uh, you know objective of all this process we have. Okay, so these are the processes that we use for extraction of metals and then purification. Okay, we'll see the extraction of metals also, like few one or two examples we'll see, like the extraction of silver we'll see, extraction of copper also we'll see. Okay, and then one important thing we'll see, that is, and then one important thing we'll see, that is Ellingham diagram. Okay, so that is again important for your board point of view also. Many times they have asked this question in the board, right? So just you write down the next one here. This is done, the extraction of this, the general thing is done. Next, you write down. I'll give you the flow sheet of this, okay, so that you can um, memorize this easily. Okay, that will be easier way. Okay. Next, you write down extraction of silver. Extraction of silver. Okay. In this, you write down this is done by the cyanide process. Name you must remember, cyanide process. The other name of this is MacArthur MacArthur and Forest process. Cyanide process or MacArthur Forest process. The ore that we use here for the extraction of silver is argentite. The formula of this is Ag2S. This also you have to memorize. Ore also they ask sometimes. Okay. The flow sheet you write down. The flow sheet of this. We have argentite ore, which is Ag2S. Now we'll do the grinding and pulverization of this to get the small, fine particles of this ore. Right. That is obviously we'll do. So I'll just write down here grinding and then pulverization. Okay. After this, we'll do what? The concentration of ore, right? Concentration of ore. The second step. Now, the process that we use here for the concentration of ore, the process that we use here for the concentration of ore, right? This process here is froth flotation process. Okay, this again you'll have to memorize froth flotation process. Okay. Now, in this froth flotation process, like I have discussed, we use some frothers, some stabilizers, and then some, um, to make that froth stable, right? All those processes that we use. Okay. Now, in this, what happens? The reaction you have here, the powdered ore plus water plus pine oil, right? I have discussed this just now. What is the purpose of this pine oil? We have examples. Air. In this reaction, it gives the froth that you form, that you get over here. Froth carries sulfide particles. Sulfide particles. So these froth are generally the carriers of these sulfide particles. Okay, which is nothing but Ag2S. Okay. Now in this, now in this cyanidation, process we use, right? What it means, what it means that this sulfide that you have, Ag2S, we are using sodium cyanide here, and that's why we are calling it as cyanidation. There are other processes also by which you can uh, do the extraction of silver, but like I discussed in the beginning, that the process we use, that process must be cost effective, right? So according to that, we'll use the extraction of any metals. Okay, there is no point wasting so much of money for the extraction of one particular type of metals, right? So we use the best process in which the cost, the input of the cost is minimum. That's the logic we have for for choosing any particular type of process. That okay. Now when this Ag2S reacts with sodium cyanide, okay, this reaction is reversible in nature. This forms a complex of sodium argentocyanide, which is NaAgCN2. Sodium argentocyanide, write down the name, plus sodium sulfide also we get here, Na2S. This Na2S, in presence of oxygen, water, converts into sodium sulfate, Na2SO4, plus hydroxide, which is NaO, where this reaction is not balanced reaction. Okay, I'm just giving you the product. Plus we'll get sulfur over here. Right now in this, just copy it down. I'll just write down in the next slide, next page. Done. Now this sodium argentocyanide that we have, from this we have, our purpose is to extract this silver. Okay, so from this silver we have to extract, and for this we use any metal you can use which is more electropositive than silver, right? Because then only the displacement reaction takes place, right? So any metal we can use here which is more electropositive than silver. Okay, so here you see in this, the next slide I'll just add, that is precipitation of silver, precipitation of Ag, and like the metal we can use here is zinc, right? Why zinc? Like I said, because this zinc is what? It is more electropositive than silver. When any electropositive metal we know that can displace the another metal which is comparatively less electropositive in nature. This is more electropositive positive than Ag. Okay, so reaction in this process, you see the sodium argentocyanide, which is NaAgCN2, react with zinc and it forms silver plus Na2ZnCN4, right? Now fusion of this metal takes place with an electrolyte, that is electro refining process, that is electrolytic refining that we have. So we'll take an electrolyte which is AgKNO3 and it forms silver metal or solid, we can write this we get after cooling. So here what happens, the anode and electrolytic refining process that we have here, electrolytic refining, in this, what cathode and anode you are taking, that you should keep in mind. You are taking here, since cathode is made up of impure metal, right? So impure, what metal we have? Silver. So impure silver Ag plate. What about anode? Oh, sorry, this is not cathode, this is anode. And anode is impure, no? Cathode will be what? It is pure silver plate, thin strip of pure Ag, right? Pure silver plate. Anode on the left hand side, cathode on the right hand side. You must like take that, revise that thing. This is on the left hand side and this was on the right hand side, the diagram that I have drawn, right? And like this, it is connected with the external source, right? And here we have the electrolyte. So this is anode and this is cathode. The larger one is anode. So anode is impure Ag plate, right? Electrolyte we can use here, that is AgNO3. AgNO3 solution plus HNO3. And in this, when the electrolysis takes place, pure silver deposited at cathode. That's what the process we have. In this reaction here, just one more point you write down. In this process, the impurities oxidized. Impurities oxidized and raised as scum on the surface, which we can separate out easily from the surface, right? So this is what the process we have for the extraction of silver. Okay, they won't ask you the, you know, maybe in board they may ask you how do we extract silver. For like competitive exam, they may ask you what is the ore we use for extraction of silver, right? What is the process name, like this MacArthur and Forrest process. Once they have asked in one competitive exam, maybe in medical NEET or any other exam, but this name they have asked once. Okay, and then what metal we can use here, like I said, zinc we are using here for the precipitation of silver. This metal must be more electropositive so that it can displace silver. Okay, so that's again one important thing we have here. Okay, now you see the next one is extraction of copper. Extraction of copper, you write down. Okay, extraction of copper. Okay, the ore that we use here is mainly copper pyrite. Copper pyrite. Okay, and we use here, the process is smelting, right? So copper pyrite, the formula is CuFeS2. Now you see the flow sheet. CuFeS2, copper pyrite. First of all, it is the grinding and pulverization, right? So it will be crushed, pulverization, right? Now in this also, the concentration of ore is done by fourth froth flotation process. Concentration of ore. First, let me draw this flow sheet, and I'll write down the key things into this. Now, the next process here is roasting. Roasting. Roasting takes place in presence of air. We have discussed already. After this, we have smelting. In blast furnace, in presence of air. Okay, so let me write down all those reactions and the points that is important here. Concentration is done by, here you write down, froth flotation process, right? And in this, we add what? Pine oil and potassium xanthate. Potassium xanthate. We'll add these two, and continuous agitation will do into this. So in this, what happens? The impurities settles down in the bottom. Because of this continuous agitation, impurities settles down. Okay. In roasting, what happens? The concentrate or concentrated ore, right? The concentrated ore heated strongly, right? And the reaction in this, we have the sulfur plus O2 gives SO2. The arsenic, all these are impurities actually. Arsenic plus O2, this is not actually that much important. I'm just giving you the reaction here, As2O3. And the other one is antimony, 3O2, 2Sb2O3. These two are actually volatile. Okay, so it can be removed easily. This SO2 also will remove over here. SO2 gas forms, it will also removed. And these two are volatile in nature, can be removed easily. Okay. Now in smelting, what happens in presence of air, right? So all these iron sulfide that we have, the various reaction we have here, right? In this you see the sulfur, arsenic, and all these presents as impurities, and then it's oxidized, and then it reacts, right? So what happens here, one more thing in roasting, is the copper pyrite that you have, which is 2CuFeS2. With oxygen, we are heating this, and the product that we get here is Cu2S plus FeS plus O2. And we have already discussed that some of the oxides, some of the sulfides in this process converts into what? Oxides, that will be Cu2O, and this FeS converts into FeO. This thing we have discussed in roasting process. So I'm not discussing those things again. Right? Now, in this smelting process, the roasted ore, right, that ore that we get from here, this process is mixed with coke and silica. Coke and silica. Now the reaction that you have here, whatever iron sulfide which is left over here, all these, suppose if it is not oxidized or converts into its oxides, so whatever it is left here, that will also converts into its oxides, like FeS forms FeO plus Cu2S, right? And then this FeO combines with this silica SiO2 forms FeSiO3, which is slag, which can be removed easily, and this Cu2S combines with oxygen forms oxide plus 2SO2. This is the reaction. Okay, this silica that you have, whatever FeO we get here, all these FeO converts into FeSiO3, and from here all iron, all Fe is removed in the form of this slag as slag. Now the next step we have here, next step here is, see, one type of question that they ask sometimes in the like exam also, that what is the purpose of adding silica here, right? So since this iron is present as an impurities, right, so this you have to remove. So when we add silica into this, all these oxides of iron converts into FeSiO3, which is a slag, fusible slag, which can be removed easily. So that is the purpose of adding silica. Most of the time, silica we add to form slag only. That's the purpose of silica to add, right? Now the next step we have here, that is Bessemer Ization. Okay. Next step you write down BESSE, Bessemer Ization process. This takes place in Bessemer converter, right? The machine that we call it as Bessemer converter. Now in this also similar kind of reaction we have, and here also some amount of silica added. The purpose is again same. If any iron oxide uh, left, that will also convert into slag. That is the purpose we have. So again, the same kind of reaction here, FeS2 plus 3O2, gives you iron oxide FeO plus 2SO2, because this process also takes place in presence of air. In presence of air, so there are chances that if any iron is left over there, that will oxidize into its uh, oxides, right? So to remove that oxide again, the silica will be added here, right? So the reaction here, that is how the iron oxide forms, and this iron oxide again reacts with SiO3, SiO2, it forms FeSiO3, right? And this copper sulfide plus 3O2 again converts here into Cu2O plus 2SO2. Same kind of reaction it is. Now in this, what happens, the important thing here, that this Cu2S and Cu2O, auto reduction takes place, right? Cu2S plus Cu2O, auto reduction takes place. So it forms what? Sulfur dioxide and copper metal we get. 6Cu, this reaction we have seen already, plus SO2, auto reduction. Okay. This copper, we call it as blister copper. Blister copper, which is 98% pure. Okay. 98% pure. Now the last method here is electrolytic refining. Again, this metal that we get, we have to refine this. So electrolytic refining. Now in this, the anode that we use, anode is again, it is impure. So again it is impure Cu, copper plate. Cathode will be pure copper plate. Electrolyte we use here, that is CuSO4 plus H2SO4. Okay, and the pure copper we get at again cathode. Deposited at cathode. Okay, so this is the again extraction of copper. Okay, so like this we can have another metal also extraction process. Okay, but again before going into that, like this, all different processes we have, and then some reactions, and what is the element or compound we are adding, what is the purpose of that, so that again you can go through any book if you have, right? So if you like iron and all, you can go through, right? But before that, since we have to discuss Ellingham also, which is important, more important than all these, because these are just, you have to memorize. You just have to see the processor and you have to memorize. General thing we have discussed, that is the only thing we are following in all these extraction processes. Okay, so first we'll discuss Ellingham here, and then possibly we'll see the another method also. Just I've given you two just now. Okay, we'll discuss first the thermodynamics of reduction processes. Reduction process. Okay, we'll take a break over here. 10 minutes break we'll take, and then we'll start this. Okay, this is important. Okay, Ellingham is important. Diagram is also important. In board also, I have seen many times they have asked question onto this. Okay, so this Ellingham diagram is important. So I'll take a break for 10 minutes. Okay, it's 4:18 now. We'll start at 4:30. Okay, we'll start at 4:30 and we'll finish this Ellingham today. Okay, we can finish this in half an hour, but there are many things into this. But yes, we'll finish this. Okay. Okay, so we'll start now. Thermodynamics of thermodynamics of reduction process. Okay, you see the thermodynamics of reduction process, which is nothing but this that also we use that reaction in what we say, the extraction of metals. Okay, so all these reactions, since we are dealing with reactions, so we must have the the thermodynamics of that reaction we should know. See, for Nikhil, for JEE mains, like we cannot say it's a complete theoretical topic, right? There is nothing logic into it. Whatever till now I'm explaining, like this is the process, froth flotation, and all these reactions are there, calcination, roasting. They only ask theoretical question into this. If you ask me, the weightage is not that much. If you ask me, like if you have to go through any question into this, just little bit of information that I gave you, and little bit of information you should have for this Ellingham diagram. Ellingham diagram is important for your board also and for JE also. But yes, if you ask me weightage, it's not. I think it's not certain, right? You cannot say anything. They may ask you one question, maximum one question. They may not ask you any question from this chapter. But yes, for board exam, this Ellingham thing is important, and again, the extraction of few elements is also important. In board, they can ask you directly, okay, write down the extraction process of silver, write down the extraction process of copper. For JEE mains, it is not that much important. Okay, so anyways, so extraction, you see in this one, the thermodynamics of a reduction process, and that we understand by Ellingham diagram. Okay, so that is what we are going to see here. So you write down the heading here. Ellingham diagram. Okay, write down few points into this, and then we'll discuss it. Right, write down. This diagram usually consists of the plot of del G and temperature. Del G naught versus temperature. This is the plot of Gibbs free energy change and temperature for various reaction. Okay. Now, since we are talking about the thermodynamics of reduction process in metallurgy, right? So we'll talk about the formation of oxides into this. Okay. See, any oxide, if it forms, right? Suppose if I write down the example here, that is 2xm solid plus it combines with O2 gas to give 2mxo solid. This is the oxide we are forming, right? So this particular diagram is actually, valid for oxides of various elements, but we can draw the similar kind of diagram for sulfides and halides also. That I'll give you after some time. But just to write down one thing here, one thing you try to understand. This oxygen is a gaseous molecule, and this is a solid molecule we are getting. So entropy is what? From gas to solid it is going. So entropy is decreasing, right? So whenever the oxide formation is there, del S of this reaction will be less than zero. Because gas to solid conversion we have, so entropy obviously decreases, right? So write down into this. This diagram is write down this diagram involves the formation of oxides of various elements, oxides of various elements, comma, similar diagram we can draw for sulfides and halides also. Similar kind of diagram we can draw for sulfides and halides also. Okay. Next line, the formation of oxides takes place by decrease in entropy, decrease in entropy, okay. So now when this is, when now you see when this del S is less than 0, so the reaction or the equation we have del G is equals to del H minus T delta S. Okay, so as temperature increases, right, this means what? T delta S, T delta S becomes more negative. Becomes more negative. This means what? Delta S is decreasing and T is increasing. So T delta S becomes more negative. It means the value of T delta S will decrease. Right? Now when the value of T delta S will decrease, so obviously del G value will increase. T delta S value is more negative, means this negative, negative, positive. So del H value will increase. Right? So del G value will increase, or we also call it as del G becomes less negative, means it is increasing. Write down next line. So the point is, as temperature increases, del G increases. That is what you have to keep in mind. Now when we see the graph, you can correlate this. Okay, but before that, you see, you write down one point here. The free energy change is the free energy change energy change the free energy change that occurs, just a second. Okay, write down the free energy change that occurs, energy change that occurs when 1 gram molecule 1 gram molecule of a common reactant of a common reactant, and in this case the common reactant is oxygen, which is oxygen in this case, because we are talking about the formation of oxide that only takes place with oxygen, right? 1 gram molecule of a common reactant is used is used the free energy change that occurs when 1 gram is used at is used, or the molecule of a common reactant is used may be plotted graphically against may be plotted graphically against temperature for a number of metals for a number of metals to their oxides. This graph is Ellingham diagram. What is the meaning of this that I have given you? You will understand when you see the diagram. This graph is Ellingham diagram. Now the important thing here is what the diagram is and what is the key features of the diagram, right? So first of all, I'll show you the diagram, okay? And then we'll see the key features of this diagram. That is important. Sometimes in the board exam, they ask what is Ellingham diagram and state some key features of Ellingham diagram, okay? So I'll show you that just a second. Okay, now you see the Ellingham diagram. See, this is the Ellingham diagram we have. Okay, so now you see this in all these diagram. The important thing is this: the relation of del G and temperature we know already. This is the del G axis we have, right? And this is the temperature. X-axis is temperature. Now for all these elements you see magnesium, aluminium, silicon, chromium, zinc and all, we have the diagram of temperature, right? So all these diagram you see, a few one or two exceptions if you leave, the slope of this line is positive, right? All these line, the slope is positive. And the value of Gibbs free energy, you see here, the value of, for all these graph, the value of Gibbs free energy increases with increase in temperature. And that is what we have discussed. What we have discussed, that this del G is equals to del H minus T delta S. Delta S decreases because the oxygen is decreases because oxygen is converting into O2 gas is converting into solid, so entropy is decreasing. So with increase in temperature, you see if you go from this side to this side, the temperature is increasing. With increase in temperature, T delta S decreases and hence del G value will increase. That